Underneath every line of JavaScript you write, a silent machinery is rapidly processing raw text into complex memory structures. This machinery operates with rules that can appear entirely contradictory. If you access a variable created with the var keyword before its declaration line, the engine doesn't crash. It quietly hands you an undefined value. Attempting that same operation with a variable declared using let causes the engine to throw a fatal reference error and halt execution immediately. The engine also manages state across time. An inner function can reference a variable from an outer function and retain that value long after the outer function has finished executing and vanished from memory. Developers frequently rely on trial and error to resolve these inconsistencies, shuffling code or relying on framework abstractions rather than investigating the engine mechanics driving the behavior. To master this system, we'll map the compiler's scoping rules, the structure of lexical environments, and the path of data through the engine's memory architecture. Understanding this compiler-level architecture allows you to move past guessing how state works and begin writing enterprise-grade, memory-efficient JavaScript. Precise execution begins with a shift in perspective. JavaScript engines do not execute your code strictly from top to bottom. They perform an initial parsing pass first. The engine operates in two distinct phases: the compile phase, where the engine parses code for structure, and the execution phase, where the runtime logic is processed. The compile phase builds the environment record. Declarations outside curly braces enter the global scope. Entering a function creates a nested record for local variables. Standalone braces trigger a block scope. Hoisting mechanically populates these records before execution begins. A variable declared with var ignores block scopes, attaching instead to the nearest function or global scope. During compilation, the engine immediately initializes these entries with a value of undefined. Variables declared with let and const follow different rules. While the engine hoists their declarations into the record and respects their block boundaries, it leaves them uninitialized. This uninitialized state creates a gap between the start of the block and the variable's actual declaration line, a region known as the temporal dead zone. If the execution phase attempts to access a let or const variable while it is in the temporal dead zone, the engine throws a reference error. Redeclaration rules further distinguish these keywords. The engine allows var to overwrite an existing entry in a scope, while let triggers a strict syntax error during the initial scan. Hoisting and initialization errors represent the engine's strict enforcement of the environment records established during the compile phase. Now that we have mapped how individual scopes are created, we can examine how these nested records communicate with one another. JavaScript uses lexical scoping, meaning a function's scope is determined by its physical location in the source code at author time. The location of invocation at runtime does not alter this resolution path. The lexical environment contains the local environment record and an outer reference pointer. When searching for a variable, the engine checks the local record first. If missing, it follows the pointer to the parent's environment, continuing this chain outward until reaching the global scope. This creates a permanent lexical binding. A function is locked to the lexical environment where it was declared for its entire lifecycle. This physical location binding governs all variable resolution, regardless of where the function is executed in the final application. Transitioning to the runtime lifecycle reveals how these permanent bindings interact with system memory and execution contexts. Let's monitor the call stack and memory heap during a nested counter function. When the outer function executes, it's pushed onto the call stack, establishing a local counter variable. Once it returns the inner function to the global scope, it's popped off the stack. Normally, local variables are destroyed by garbage collection when their parent function finishes. Closures are the exception. Because the inner function maintains its permanent lexical environment reference, this outer pointer prevents the garbage collector from destroying the counter variable. This creates exclusive data privacy. The variable remains isolated in the heap, reachable only by the inner function holding the reference. This mechanical logic explains common interview pitfalls. Consider a for loop using var to schedule a series of set timeout callbacks. At runtime, this loop logs the final value of the iterator 10 times, instead of counting from 0 to 9. Because var is function scoped, every callback shares the exact same lexical environment. By the time the callbacks execute, they all reference the single final mutated state of the variable. Replacing var with lec forces the engine to generate a unique, isolated block scope for every iteration of the loop, providing each callback with its own independent variable reference. Closures emerge when the engine's garbage collector is forced to respect an active lexical reference, preserving a data path that would otherwise be destroyed. Viewed as a unified whole, the JavaScript execution system relies entirely on the precise coordination of these internal structures. The compiler maps scopes into environment records and enforces the specific rules governing var, let, and the temporal dead zone. Lexical environments then permanently lock those isolated scopes together based on their original author time location in the source code. Closures are the functional result of these connections, functions that maintain access to their original environments. In JavaScript, a function's memory of its environment is dictated entirely by its origin. Treating JavaScript as a three-dimensional architecture of memory environments rather than a flat script changes how you diagnose state and design for scale.